Okay, good morning, guys, again. Everything seems to be working, recording. Okay, so today is Monday schedule, right? And tomorrow there will be another recitation class. So the next lecture is going to be only on Thursday. So where we are, you remember we started moving, since it was a long weekend, so we need to refresh. We started moving towards simple circuits. And as the first step, we introduced batteries, then we introduced capacitors, and now we're in the process of introducing current and resistors, right? So actually current we introduced in the lecture, so let's review that, but we haven't introduced resistance, so we have to introduce it now, right? And also some new stuff will be introduced tomorrow because we didn't have lectures. Okay, so let's assume that we have some piece of a conductor. So let's assume that we have this piece of a conductor, right? And let's assume that we applied the potential difference, delta V. Of course, if you apply the potential difference, current will start flowing as a consequence, right? So the reason is the potential difference, consequence is current flowing, right? So now, how can we define current? So in order to define current, we have to pick a cross-sectional area, for example, over here, right? And observe how much charge flows through that cross-sectional area in a period of time, for example, infinitesimally short period of time, dt. And let's say this amount of charge, right, dq, crossed that cross-sectional area in this period of time. So as a result, current is defined as dq over dt. Right? The amount of charge which crossed a cross-sectional area in the period of dt, infinitesimally small period of time. That is in instantaneous current. Okay, let me frame it. Right. And instantaneous current and special unit, SI unit, amps, amperes. It's one of the fundamental, one of the basic units. You remember in physics 1 we had kilograms, meters, seconds, and now amps, amperes, right? Basic units. Okay, so that's definition of the current. Let me separate it sort of like this. And now direction of current. Current direction. Direction of I. Okay, if you have, for example, some arbitrary circuit, completely arbitrary. Let's say you have some device and which is connected to a battery. Of course, this longer bar represents the positive electrode, smaller one negative electrode, right? And so by convention, direction of current, it's a motion, effective motion of positive charges. And of course, positive charges would flow, of course, they don't flow, effective motion, right? From plus to minus. Again, it's effective motion of positive charges. So as a result, current flows from plus to minus. So that's current. Okay, so let me write it. So I flows from plus to minus. Again, it's a convention. It's a convention. We discussed that convention thoroughly in the lecture. The same convention as like we used to introduce the electric field lines. Electric field lines, they start on positive charges and end on the negative charges. So from plus to minus. Here the same, from plus to minus. Although we all know that actual electrons actually moves, right? Not positive charges. So that direction. And now, we also need to introduce current density, right? I skipped that. That's why I need to often check my notes. current density. Okay, maybe I'll write it here. So also we can introduce current density. So it is introduced as J equals current divided by the cross-sectional area over which that current is measured, right? So that's our current density. Right. So there are no any special units. So whatever you see here, amps divided by meters to the power of 2. Okay, let me separate this small section. And now, big one, conservation of current. So let's introduce conservation of current. And there are two parts. The first one, what if you have a wire and there are no junction points? Junction point is a point where current gets split or currents are merged, right? So if no junction points, no junction point or points, in that case, it doesn't matter where you measured your current at this cross-sectional area, or here or there, it doesn't matter. Current is going to be the same. It's like water flowing through pipes. If pipe is wider, of course, water flows slower, right? But in the where the cross-sectional area is small, of course, water flows faster, right? And over the same period of time gives you exactly the same amount of water if you measure it where the cross-sectional area is larger and where the cross-sectional area is smaller. Right? Amount of water per unit time will be exactly the same. Right, so no junction points. If I draw something like this, right, so let's assume that this is the wire, right, and so current will be exactly the same. So it doesn't matter if you measure it, if you use this cross-sectional area or over here or over there, current is going to be exactly the same. Right? Again, you remember, in order to measure current, you need to choose a cross-sectional area and do these manipulations. Right? It doesn't matter if you measure it here, here, there, current is the same. So what should I write? So in this case, I is the same at all points. Right, and now what if there is a junction point, right? So with a junction point, so what if we have a junction point? And for example, let's say you have a wire, and over here somewhere there's another one. So this is the junction point. So in this case, total amount of charge entering, total amount of current entering the junction point must be equal to the total amount of current leaving junction point. Okay, let me draw it here. Let's say something like this. So the total amount of current in must be equal to the total amount of current out of the junction point. Right. So let's say it can be I in, this is I out 1, and this is I out 2. So this equals this plus that. Conservation of current in the presence of a junction point. Now, let's separate this. And now, let's introduce one law, which is very important. So let's assume that we have some piece of wire. Probably I'll draw it here. So piece of wire, right? And you apply the potential difference, delta V. Of course, as a result, it's like this picture. Current flows as a result. And now if you start playing with these parameters, delta V, reason, I, consequence, of course if you increase delta V, current will go up. If you increase delta V even more, current increases more. Delta V more, current more, and so on, right? Of course, if both parameters increases, it makes sense to check, what about the ratio? And the ratio happens to be exactly the same. So if you take a ratio of delta V versus current, you're going to get exactly the same number. It doesn't matter what is delta V and what is I, right? So if that is the same, if that ratio is the same, all right, for this particular conductor, it means that that number is some sort of intrinsic property of that conductor, of that object, right? So if that intrinsic property, that might be useful for us. Let's give it a nice name and use it. And that's what resistance is. Resistance, it's a ratio of the potential difference versus current. So as a result, we can write, so R equals, by definition, right? That's how we define it. It's a delta V over I. And that's what we call resistance. Right. Okay, let me frame it because that's an important formula. So you see now, I introduce it in a similar way like we introduced capacitance. You remember capacitance was introduced as Q over delta V, charge on electrodes divided by the potential difference across electrodes. Now here we introduce as delta V versus I, right? Again, you see three parameters are involved. That circuit trinity, right? So if you want to know everything about the resistor, you need to analyze these three parameters. Once you know them, basically you know everything about the resistor. Three parameters again. Right? What else? Yeah, units. Right. So resistance is used a lot. So of course it makes sense to give a special unit, ohms. It's a capital omega, right? Ohms. Okay, there's no point of apostrophe, just ohm, right? Units of ohm. All right, so what else I should mention? Yeah, symbol. In the circuits, of course, this is used every time. Whenever I try to draw it, it looks ugly, right? So that's what resistance. In Europe, it's just a rectangle. It's less lines, faster to draw, and usually it looks less ugly, right? Whenever I try to draw this, it's more complicated for me, right? Okay, so that's the resistance. Okay, I mentioned this, yeah. So now, next, let's look inside of this resistance, right? Look inside of R. So let's look inside of R, and I will put a new bullet. Oh, for example, let's say we have some, again, conductor, right, of some length L, cross-sectional area A, right? And so let's find out which parameters might be involved in R. Basically, we just want to dive inside and see what might R depend on. Right. Okay, and what I'm going to do right now, it's not a proof. It's more like a justification. Of course, it can be proved what we're going to write, but I don't want to spend time and getting into that microscopic picture of the conduction and so on. Right? So let me just give you these justifications. First of all, what if we have two conductors made out of the same material, the same cross-sectional area, right? You see, the same cross-sectional area, but different length. This is smaller, this is longer. I mean, larger. Right? Which one is going to have larger resistance? Usually students don't have any troubles giving me the right answer, right? It's obvious. The longer one is going to have larger resistance. And justification is quite simple, because what is resistance, sort of on a microscopic, from the microscopic point of view? Electrons current, which give us current, right? They do not fly in an empty space. They fly through a crystalline structure, metal. It has some structure, right? Crystalline structure, which of course consists of gazillion number of nuclei. So electron gets accelerated by the potential difference, right? Starts flying, and of course sooner or later, actually very soon, it will collide with one of those nucleus. Collision, concussion, recovery, then again acceleration in a slightly different direction, but still approximately that way. And again, very soon it will collide with the next nucleus, right? Then again, collision, concussion, recovery, again, and another collision, and so on, right? The longer the resistor, the more collisions electron is going to experience. It's like if you try to run along a straight line through through the forest, right? So if you run along a straight line, very soon you will collide with the first tree. After recovery, and again, if you start running straight, very soon you will collide with the next, another tree, and then another tree, and another tree. And of course, the longer the forest, more collisions you're going to experience, right? The more concussions you're going to get. So it's exactly the same story with electrons. So the longer resistor, the larger the resistance. All right, so it means that the length of the conductor of the resistor must be in the numerator, L. Now, the next one. Again, this is just from optical lab, just the posts to keep optical elements on the optical table, right? The same material, the same steel, the same length, but this has a larger cross-sectional area, this has a smaller cross-sectional area. So the question is, which one is going to have larger resistance or smaller resistance, right? And here, with this question, students very often give me the wrong answer, quite often. So let's justify this situation. Which resistor is going to have larger resistance or smaller resistance? Let's imagine this situation. 8 a.m., rush hour in Boston, everyone going to work, right? And let's imagine ourselves on some subway station, for example, downtown crossing. Of course, that platform will be filled with people, right? Okay, let's imagine train comes, those doors get open, and of course all these people start squeezing in with lots of resistance, lots of pushing, elbowing, right? Coffee, right? Spilling, right? So yeah, they will be able to get through, but with plenty of resistance. But now let's imagine a different situation. What if this new progressive train comes, and the whole front wall of the train, of the train, right? The whole wall just gets lifted. In this case, doors basically are gigantic, and all these people on the platform, they can just step in the car or in the train without any significant troubles. Maybe near the edges, right? There will be some troubles. But overall resistance will be much smaller because the cross-sectional area is larger. And the same with these conductors. So the larger cross-sectional area, the smaller resistance is. So it means that if I want to put cross-sectional area into my formula, it must be in the denominator downstairs. All right? So as a result, I'll put A downstairs. And the last parameter. Obviously, let's say if I have a resistor made of like this steel and a resistor made of gold, they obviously must have different resistances. Yeah, their resistance must be different. And obviously, gold will have less resistance, right? So resistance also depends on the material. Right? So there must be a parameter describing material. And again, and now it's up to us, up to researchers, where to introduce that parameter. Very often, resistivity is introduced. And that resistivity, which is usually measured, not usually, which is measured experimentally, right? is in the numerator. But in the physics of semiconductors, they prefer to use different parameter, conductivity, and that conductivity is in the denominator. Okay, we're going to use resistivity, rho, right? And so how can you find that rho? Open the book, reference book. Okay, copper, this number, aluminum, this number, gold, this number, tungsten, that. If it's a alloy of this with that, percentages are given, so that will be the resistivity, right? There are thick books with those numbers. So resistivity is usually measured experimentally. You just hire a cheap labor graduate student, right? And he will measure or she will measure everything, right? So rho. And now instead of sign of proportionality, I can put equal. So that's what we need. So that's what is inside of resistance. Resistivity, L, length divided by cross-sectional area. And look, does it depend on the electric field? Current? No. Potential difference? No. Charge? No. Nothing. It depends on what? Rho describes material. Length, geometry. Area, geometry. Basically, it depends only on the geometry and material. We've seen something like this in the past. You remember when we introduced capacitance of a parallel plate capacitor? We had C equals epsilon naught A divided by D. And again, that formula depended only on the geometry and the material. And here the same story. All right? Depends only on the geometry. And that's why if you build the resistor, you can label it, because you can measure it, you can easily calculate. And the same story was with a capacitor. Right? Okay, very similar. Right? Okay, that's what I wanted to mention. Right? Okay, maybe I should write. So it depends on geometry. Depends on geometry. Just to emphasize on that. All right, so what else should I mention? Yeah. Resistance, resistivity. They are not the same, of course, right? Resistivity, rho, it's a property of a material. Gold, resistivity. Copper, resistivity. Aluminum, resistivity. Silver, resistivity, right? Resistance, it's a property of an object, of a conductor, of a resistor, which has a certain geometry, has made out of certain material, right? Again, rho, property of a material, resistivity, property of an object, of a resistor, right? So don't get confused, don't be confused with these two different quantities, right? Okay, so that's what I wanted to review, and now a few problems. So first one, chapter 27, so 2711. It sounds like 7-Eleven, right? Sure. Right. So that's problem 11. So what we have here, an integrated circuit is given. It sounds so fancy, but for us, it's just nothing but a slab of a material. And current flows through this slab. Right. But anyway, it sounds cool, so let me write integrated circuit. Integrated circuit. Geometry is given. Let me draw the picture probably first. Oops. Wrong direction. Right. So, geometry. A by B. This width is A, or height A, width is B. So those are given. So A is 2.5 micrometers, B is 75 micrometers, right? Then current density is given, not current. It's quite common, for example, like I work with semiconductor lasers, quantum cascade lasers, right? And if you read the paper, usually they don't give current. You have to drive the current through the semiconductor, basically slab, right? Because different groups, they made lasers of different cross-sectional area. So giving current, it's not very smart and convenient. So everyone just give current density. And then if you want to compare it's easier to compare than your results with results obtained by a different group. So current density quite often is given, right? Especially in the cases like this. And again, if you want to know current, okay, take current density, multiply by the cross-sectional area, it will be current, your current. So current density, J, is equal, that's J, right? So that's number 75, or 7.5. 7.5 times 10 to the power of 5 amps divided by meters to the power of 2 square meters. Right, and so what we need to find? We need to find, of course, a current flows, so there will be, of course, charge flow through this structure. We just need to calculate the amount of charge flown through this element in 15 minutes. So let me write. So we need to find Q in delta T equals 15 minutes. Right? Right, so let's just look at where we have a charge. Where do we have a charge? Nowhere but in the definition of current. And again, this is instantaneous current. So you observe charge over infinitesimally short period of time. But in our case, we observe over finite period of time. 15 minutes, it's not infinitesimally small, right? So, of course, we will write the formula, and instead of dq, we're going to use q. It's some finite amount of charge which crosses our element in 15 minutes. Right. So I will write. So basically, we're going to use sort of like an average expression for an average current. But if this current is constant, then average current, instantaneous current is going to be the same, right? So I equals Q over delta T. And Q, that's what we need to find. So, of course, we can solve it for Q. So it will be I times delta T. All right, so can we find current? No. Current density is given. Finding current is trivial. J times A, right? Simple manipulations of a basically, it's not an alphabet. It's alphabet over circuitry, right? So we need to get through this. All right, so current will be equal to J times A. And since geometry is given, we can find cross-sectional area. So it's A times B. So it is equal to J times A times B. Okay, let me close my explanation box, and basically we're almost done. Right, so it will be J times A times B times delta T. Micro 10 to the power of minus 6. And here there's only one, okay, I don't know, it's not a trick. It's not a hidden rock, but of course, use seconds. Well, you're not supposed to use minutes, right? So of course, you need to convert it into seconds. So it will be what? 15 minutes times what? 60 seconds divided by 1 minute. Right. So of course, you have to convert. Don't forget. Sometimes students make... Yeah.
Could you do something that would signify the difference between amps and area, because they look the same for...
It's in this case, since book uses a, right, and I don't want to change units. I mean, the way we denote units, right? Because when you start reading the book, you will be also, it will create a mess in your head, right? So you need to, very often we use the same symbols, right, to denote different quantities. You just need to get used to, right? I don't feel like changing, right, the units, because again, if you open different books, different symbols, right, it creates lots of confusion. So I don't feel like changing it. Of course, we can use here, for example, S capital, but since book doesn't use S capital, so try to sort of feel the difference. Sorry, but yeah, so far you're the first one who asked, right? And I'm sure that some of you get confused, but you need to develop this, not a habit, but see which symbol what's the meaning of which symbol, right? Because there are plenty of situations like this in physics. Okay, but I will think, since you triggered this, right? You raised this question, so I will think. And so far, no one brought it up. So as a result, I never thought about doing anything about this. Okay, okay. So for now, usually amps, it's after the value at 5 amps, right? 7 amps, but this is in the formula, right? This is in the formula. Of course, here amps will never be. Okay, it's a growing process, right? Sooner or later, you will feel the difference, and you wouldn't be confused with this. Trust me, right? We all went through that. So, okay, I'm not going to plug numbers, so I will just write the answer. It will be 0.127 coulombs. I don't know why, but in the previous section, students not complain, but challenged that they got 0.0127. But in my notes, it's this number, and so far, that was correct. I will check after classes, right? But so far, I trusted my calculations, and this seemed to be correct. But in the previous class, students challenged me, right? But I don't want to waste time using calculator. So now that's the problem. I added one additional question. We need to answer how many electrons cross this structure in this period of time, because there will be similar question about electrons in your homework. So I decided to add this. And okay, so this part is quite simple, because this charge, it's a basically a flow of electrons, right? Gazillion number of electrons, right? And each electron carries charge, which we know, 1.6 times 10 to the power of minus 19 coulombs, right? So Q, this Q, it's a number of electrons times charge of one electron. That's what Q is, right? So now if we want to know the number of electrons, just the total charge divided by the charge of one electron, right? So N will be equal Q divided by the charge of one electron. So it's a 0.127 coulombs divided by 1.6 times 10 to the power of minus 19 coulombs. So what's the number? 7.9. It's, of course, a gigantic number. 7.9 times 10 to the power of 17 electrons. Right. Again, this additional question, which I added to this problem. Problem was done at that point. Okay, So usually, based on my experience, students don't have significant troubles. Anyone who does anything in class, right, don't have any troubles with this, with the problem about finding current density, resistance. Usually students feel comfortable. Okay, but if you have any other suggestions or questions, okay, go ahead. Otherwise, the next problem, 31. Let me start erasing something at the top. I don't want to erase this review because we need all this alphabet of circuitry. Right, so this is 31. So what do we have in this problem? A wire, 100 meters long wire. Guess what it's made of? Gold. Right, there are plenty of problems in this book about gold. It looks like the author likes gold a lot. Right? Gold here, gold there. Right, gold rush. And so basically it's sort of like a spool, 100 meters long wire. Right, small diameter. Of course, it's a spool. In photonic centers, usually they have a spool of gold wire, so they can use wire some lasers. Right, so it's quite common, right? All right, so that spool of wire is connected to a small battery. So we will have to find current flowing through the device, or through the wire, All right, so this is problem 31. So we have a 100 meters long gold wire. Okay, of course I don't want to draw spool of wire, too complicated. I'm going to draw just a small cylinder and assume that this is my 100 meters long wire. Right. Okay, let me show that this is L, 100 meters. Right. Then cross-sectional, oh no, not cross-sectional area, diameter is given. D is, yeah, it's a wire, so it's a small point. Diameter is small point, 1 millimeter. And it's gold. And then, as I said, it is connected to a battery. Right. Of course, longer bar represents the positive electrode, smaller one, negative electrode. So, of course, current flows from plus to minus according to that convention. So current, of course, will flow this way. And we need to find that current. So battery, what information about the battery? So it's a watch battery, 0.7 volt. So delta V, 0.7 volts. Right. So what we need to find? As I said, we need to find the current flowing through this wire. Right. So basically, our wire just a resistor, right? And if you want to analyze any resistor, you have to play with 3 parameters every time, right? You remember, like with capacitor. With capacitor, we had CQ delta V. Now RI delta V. 3 parameters again, right? 3 parameters. Okay, let me start. R, I, delta V. Right, delta V. So let's look at each of these parameters separately. And also, we need to use formulas which connects them all. Right? So first, R. Of course, R depends on what? We just discussed. It depends only on the geometry. Since geometry is given and material is given, we should be able to find resistance of the wire, right? So it depends on geometry. And that is given, so of course we should be able to find resistance, right? So yeah, we should be able to find it. Then, what's next? Current. current. That's our goal. That's what we need to find, right? And then the last one, delta V. And delta V is actually given potential difference across the wire given, right? And then every time we have to also use the formula connecting these three parameters. It's the same like with capacitor, CQ delta V. Every time we analyze C, Q, delta V, and then formula which connects them all. And R equals delta V over I. Formula connecting them. Formula connecting all these three parameters, right? So basically, yeah, we should be able to find resistance because geometry is given. And then these two guys are connected through this formula. So we should be able to get I by just playing with delta V over R. So two-step problem, right? Right. Okay, so let me separate this sort of discussion of three parameters. And now let's get into the details, right? So first, resistance, rho. Okay, rho, gold is given. Gold, information about the material is given. And so please use, don't try, use the book. Don't use Google to find resistivity. Right? All right, so rho of gold equals, all right, so let me, okay, it's a 2.4 times 10 to the power of minus 8 ohms times meters. Okay, that can be found in table 27.2. Right. That information can be found from that table. Google can give you slightly different numbers, so try to use a book because mastering physics programmed using numbers from the book. All right, so rho L over A, so rho, and of course A is the cross-sectional area, right? L, and now at this point, some students make very, very silly mistakes, right? So of course it's an area, it's a pi r squared because the cross-sectional area is a circular, right? So it's a pi d over 2 squared. Plenty of mistakes with these simple formulas of area of a circle, circumference, volume of a sphere, surface of a sphere, lots of unnecessary mistakes at this point, so be careful. So in this case, 4 goes upstairs and d to the power of 2 in the denominator. So it will be rho 4L over pi d squared. Okay, everything must be in meters, right? So if you convert it, you will end up with 305.6 units. It's just a resistance, units of ohm. Where is it? Yeah, units of ohm. Right. And now Ohm's law can be used to find current, right? So basically two-step problem. I equals to delta V over R, right? So delta V 0.7, R is found. Right, so you will get 0.7 volts divided by that 305.6 ohms, and that will be 2.3 milliamps. 2.3 milliamps. And I will emphasize, next class we're going to solve a few problems about current resistances, right? And I will emphasize on these three parameters, like that circuit trinity which I mentioned. In capacitors, CQ delta V and the formula connecting them. Here, RI delta V and Ohm's law formula connecting them. Right? And similar, we're going to have about inductors maybe in a month or so. Again, 3 parameters every time. Okay, so that's the second problem. And again, usually on the exam, if I give a problem like this, most of students do well, right? So, Now, the next. I need to start erasing this. Okay. So now more like a conceptual questions. Not more, it's a conceptual question, questions from the book. CQ, conceptual question 9. And in part A, CQ 9, conceptual question. We have this wire. Oh, I need to move closer so it would look less ugly. Okay, first section of the wire, second section of the wire. Current flows through this structure. It's basically this. Right. First, in part A, we need to answer about currents. So what about I1 and I2? Current in the first wire and current in the second. As we discussed in the conservation of current, when there is no any junction points, current is the same. It doesn't matter which shape and what's the cross-sectional area. If there are no any junction points, then current is the same. So in this case, I1 equals to I2. Right? So we can just label it just I. Right? So current is going to be exactly the same, I. But in part B, what about current densities? J1 and J2, which one is larger or which one is smaller? Maybe they're the same. With current densities, guys, careful, right? Because I used to give a quiz on that, and very often students, not very often, some students who don't pay attention made a mistake. So in this case, let's write definition. Definition, I over A. A is the cross-sectional area, right? So it's a J1, it's a I1 over A1. And of the second part, it's a I2 over A2. Currents are the same. So these are the same, right? Currents, but areas, of course, different. And obviously, A1 is smaller than A2 because it's given. So A1 is smaller than A2. And since areas are downstairs in the denominators, so smaller value of A gives us larger value of J, current density. So J1 is going to be larger than J2. Right? So as a result, this is going to give us this sign. Right? It's simple analysis, right? If a student is careful, no troubles. Right? Okay, now the next quick, we still have a couple of minutes. This is, in the book, there are some parts which are called stop to think. Right. Stop to think. 27.4. 27.4. We have a junction point with a bunch of wires. It looks like 5 of them. So let me draw 1, 2, 3, 4. Let me get some space for the 5. Fifth one. 1, 2, 3, 4, 5. Yeah. So junction point and some currents. 3 amp of current entering the junction point, then 6 out, then 4 in. This is unknown, and this one 2 amps out. So we need to find current and value of the current and direction at this one. Okay, just 1 minute. It should be enough, right? So we just need to use conservation of current in the presence of the junction point. Total amount of current in must be equal to the total amount of current out. All right. So now, in order to apply this formula properly, let's make an assumption, because we don't know anything about this current. If it's out or in, who knows? But we have 50% chances of getting it right. It's a huge percentage. So let's use it. Like gamblers, right? Yeah, it's actually like gamblers. So let's assume a direction of current. Let's assume, for example, in my notes, I assumed it's out. I have no idea. But if I made an assumption, write this formula properly, solve it for the value of the current. If my current happens to be positive, okay, my assumption was correct. If my value of the current would be negative, okay, bigger deal. So flip direction of the current, you see the value of the current and just change the direction and you're all set. Right? 50% is a huge percentage. So we're going to use it. We're going to assume our current direction very often. So assume Ix is out, I think. Yeah, out. Gambling. All right, so as a result, if that is out, so let's count int 3, 4. 3 amps plus 4 amps. That's this side of the equation. Now out 6 unknown current into 6 amps plus 2 amps and plus our unknown current. Okay, so solve it. Here we have 7, here we have 8. So it means that Ix is -1. So I sub x minus 1 amp. Okay, so it means that the value of the current is 1 amp, and minus indicates that I'm a bad gambler. So my assumption is wrong, right? So but what a big deal. We solved the problem. So it means that Ix is, damn it. Ix is in. It's just difficult to write near the board. I mean, near the surface, right? Okay. And of course, the value is 1 amp. Problem is solved. Okay, guys, thank you. I hold you a couple of minutes.
Glows like the sun. Watching the world seems happy and young.